Hi, my name is Ryan Stelzlenny, and I'm a software engineer on the Omniverse team. In this video, we'll discuss some of the things that make USD unique. This video is geared towards users who are familiar with graphics data formats, but new to USD. The goal is to talk about why USD is a unique and useful format. First, let's discuss some things about USD that are common with other file formats. The USD file, which is often called a layer, is a lot like other graphics files. A single file can contain models, meshes, lights, shaders, other useful graphics primitives. This render is taken from the NVIDIA Marbles demo and was built entirely in Omniverse, and it uses USD files to represent all of its data. A USD file can have multiple representations. The most common is a file with a USD extension. These are usually binary files. The binary file format for USD is called a crate file. We also have a USDC extension, and it's a nicely compressed and memory mapped fast access file format. The USDA file format is a human readable text format. Any USD file can be converted into USDA. This can be useful to understand what's in a USD file without rendering it, and for debugging and experimenting. USDA files can be opened and rendered just like USD files, and they can also be stored with a USD extension, just like crate files. USD offers other file formats as well. A USD-Z file is actually a zip archive. It contains a USD layer and its supporting files like textures for rendering. Finally, USD can be extended to add support for other file formats. All file formats are provided by plugins in USD, and you can obviously provide new plugins. For instance, Google provided a plugin to read and write meshes with Draco compression in a DRC file. I wanted to mention all the backing file formats that are available. For the rest of this presentation, I'll just be showing the USDA text format. This is a screenshot of a USD file that I dumped out to text just to give an example of what a production file might look like. This file is maybe more interesting for our purposes, though. So I've created a very simple USD file that just contains a light and a cube. Here, I've put the text of the file. You can see that we have defined a transform called world. We've also defined a light called default light and a mesh called cube. You can see in the render that we have a cube at the origin, and it's nicely lit from the front by our light. This is a render out of Create, the Omniverse tool. And if you look at the text of the mesh, it has all the sort of properties you might expect a mesh to have, like vertex counts and indices and normals, has a display color. It's sort of a basic graphics file like you might see in other file formats. So I promised to talk about what makes USD unique, but so far, I've only talked about things that are easily accomplished in other kinds of graphics files. I think one of the most interesting features of USD is this idea of layer composition. Layer composition refers to the ways USD files can be combined together. There are a number of ways you can combine USD files, and these are usually referred to as composition arcs. There are 6 kinds of composition arcs in USD. A common one is sublayers. When you hear people say that USD layers are like Photoshop layers, they're referring to sublayers. Sublayers in USD define a stack of USD layers. The stack is in strength order, and sublayers can override each other. So if 2 sublayers have values for the same attribute, the strongest sublayer wins. We'll get into some examples shortly. References are another kind of composition arc. A reference is used to add new items into your scene. For instance, if you have a chair model and you want 4 chairs around a table, you could add 4 references to the chair model. We'll also go over an example of that. The rest of these I won't provide examples for, but I wanted to go over them to give an idea of what's possible. A payload is like a reference that can be loaded in a deferred way. So you can open a scene and then choose which items in the scene you want to load into memory. A variant set, or a variant, is for switching between items in a collection. If our chair model had a weathered version, a wood version, and an Eames chair version, a variant would let us choose between them. Inherits work kind of like classes in an object-oriented programming language. If you define a class of items like humans, all humans might have an eye color. You could have your human prims inherit from that class, and they'd automatically get the shared eye color. Finally, specializes work like inherits, but they have some subtle differences that might be too specific for our discussion today. It suffices to say that they are another version of inherits. So let's dig into an example on sublayers. Suppose I have the cube we defined earlier, and it's in a file called cube.usda. Also, let's say someone else made cube.usda, and they would appreciate it if I don't change it. But I need a blue cube for my use. One way to accomplish this is to use sublayers and edit the cube in a non-destructive way. For this example, I'll create a cube_model.usda file and give it 2 sublayers. Here's that example in action. I created the 2 files on the left and opened cube_model.usda in create and got the render on the right. Here I haven't had to edit down these USDA files at all. This is really the entire text of the files that I used. So if you look at cube_model.usda, it has nothing in it other than this list of sublayers. Notice they're in strength order, so blue cube by coming first is stronger than cube, which comes second. So what this says is in the current directory, the file bluecube.usda is my strongest sublayer, file cube.usda is my weaker sublayer. And then in bluecube.usda, I've introduced the new keyword here, over, which is short for override. If you remember before, we had def or define here. So here I'm saying in the bluecube.usda file, override the transform called world, and override the mesh called cube, and give the mesh a new display color and make it blue. And we get this nice render here where we have a blue cube lit from the front, much like before. So now let's talk about the second composition arc I want to touch on, references. Sublayers are for non-destructively editing an asset. References are for combining assets together. So let's say I want to create a scene with a collection of models. For our purposes, we'll make a scene with 3 of our cube models in it. One way to do that in USD is to use references. Here, I've created 3 cubes called cube 1, 2, and 3, and each one is referencing the cube_model.usda file we created on the previous slides. This way, it'll get our blue cube. One nice side effect of this setup is that the cube model asset is only loaded into memory once. Each reference to the same thing can reuse the layers that are already loaded. So here's that in practice. Again, the entire text of the USD file fits on this slide. I made this file and opened it in Create and got the render on the right-hand side. As you can see, I've defined 3 primitives. Each one references the cube_model.usda file we created earlier. There are a few interesting things to point out here. One, notice that it says def cube1 to define a cube1, but it doesn't indicate that it is a mesh primitive. This is because we can infer the type from the object that we referenced. Secondly, if you look at the reference path, notice that it has a file path for cube_model.usda in the current directory, and it also has a prim path to world/cube. This indicates that I want to reference the cube in cube_model.usda only. I do not also reference the light. You can see this reflected in the render. The cubes are not lit from the front anymore, since I've left the light behind in the other file. This can be useful, for instance, if I want to light this scene differently than the source where these cubes came from. Lastly, notice that I've set a translation on the second 2 cubes to slide them down the x-axis and separate them in space. By doing this, in the text here, I have overridden the transform on the cube that I brought in, which was just at the origin. You could override other attributes the same way. For instance, I could set the color, or change the points, or really do any other kind of changes I'd like to do here, including adding new geometry or assigning a shader. Let's think about what this all means in practice. In our example, we've built this network of files. When you open myscene.usda in a tool that reads USD files, it will first open myscene.usda and scan it for composition arcs. It will find a reference to cube_model.usda, so it then opens that file. While reading that file, it will notice that there are sublayers, and that each of those needs to be opened. Those have no composition arcs, so the traversal ends, and we have all the data we need to render this asset. This is a simple example, but you can imagine that much more complex scenes could be created. Cube.usda might have its own references, and those references might have sublayers. There could be classes and inheritance in this diagram. A complex scene could expand into hundreds or even thousands of files. In modern filmmaking pipelines, thousands of files is actually common. This is a great strength of USD. The person or team making cube model can make their asset as simple or as complicated as necessary. And whoever creates my scene doesn't need to know or care how the model was built. Similarly, to an end user who opens my scene, they can edit properties on any of the assets here without needing to understand any of the complexity of the assets or of the pipeline that we built using these composition arcs. One other thing to mention here is that USD is heavily optimized for this type of usage. It has caches and other acceleration data structures to make this fast and memory efficient. USD's layer composition algorithm is one of the most unique things about USD. It enables all kinds of advanced workflows and makes it possible to develop flexible pipelines. In learning about USD, you may see this algorithm referred to using the acronym LIVRPS, sometimes pronounced liver peas. Composition is one big advantage to USD, but it's certainly not the only one. More and more graphics tools and renderers add support for USD all the time. It's open source and adoption is growing quickly. So by choosing USD as a data format, you can benefit from a groundswell of new tools and features that are always growing. The libraries that support USD are heavily pluggable and extensible. So if you can do in-house software development, USD and Omniverse can enable you to build advanced tools very quickly. I hope this gives you some insight into what makes USD unique and valuable. Omniverse is built on USD because we believe in the promise and future of this technology. If you're just starting to explore Omniverse, then welcome. We really hope you enjoy your time here. We cannot wait to see what you build. Thanks for listening.